Hey everybody, welcome to Math and Science. We're doing a distance learning flipped classroom lesson all about Chapter 9. Really we're just concentrating on the beginning parts, really just first 4 pages, which are on work and power. So this is an extension of what we've been doing all year. You're going to want to definitely check back to the video that we just watched and do some notes on sports science power. That goes through some problems, and this one will too. So there'll be some overlap. Hopefully we'll extend on what was covered in that video, help you out, and it'll allow you to make sure that you know exactly what's going on for homework. That being said, when something is missing or confusing, definitely send an email, talk about our next class, or just put a comment or a question in the comments below. So some context. First off, where we're going in the end is to our, this is actually Chapter 9, even though it says 6 on there, work and power, and our 2 new equations, which are that work is force times distance, and that power is the rate at which work is done, or work divided by time. So if we zoom back out on that, we'll see at the end 1, 2, and 3 example problems that we're going to go through. Hopefully those will help you out. All right, so where did we come from? You can see over here just the extensive list of formulas that we've been working on. Right, we had just finished up with momentum in here. Where we're going to start off, really the scope of this video is just in on these 2 formulas. So work is force times distance, and power is work divided by time. Note the letters. So the variables that are written here are important. We've got capital W, capital F, lowercase d. So capital W, not to be confused with lowercase w, and capital P, not to be confused with lowercase p, which we just finished with momentum. Alright, speaking of which, really cool Polynesian saying that says you can only know where you are if you know where you've come from, which again is why we're looking at these formulas and seeing the scope of the year so far. Also want to give special note to our problem solving strategies. We're going to want to keep using those. Alright, so conceptual physics, again, big emphasis on exploration, concept development, and then applying it. This is just a recorded lecture. So this is what we would do in class for lecture. We're going to apply it with part of your homework for the problems, and then a personal power challenge that we'll do at the end, and then some labs that I'll go back into school and record for you that you do in class. Another key important note for these lectures is there'll be plenty of times when you are expected to stop, pause the video, and do some work, and then come back to it. I'll let you know when those show up. The sections for this video, we're just doing 9.1 and 9.2 for now. Now the sections that we will ultimately be responsible for will be 9.1, 9.2, all the way through 9.7. So the next section really for us will cover energy, both gravitational potential energy and kinetic energy. So that's what's next. For now, we're just on work and power. Here are the pages in the book. Interesting thing to consider be what you might be able to do at home. If you can do this Discover, then pause it right now, check this out. Note too that I ended up taking a scan of the teacher's edition, so you can see some of the main objectives here. The only sections that we're covering for now are 9.1 and 2. Here we got a lot of what you saw already in the work and power video. You can see some of the units that are involved and the formula. You see over on the side some teaching tips, so things that they're trying to remind me as your teacher to cover. So we'll do that when we do labs, and you can go ahead and pause it and take a look right now, or follow along with your book. That's actually probably your best bet. Here's our next page. Again, definition of work, what's going on with units, what are the formulas, and then we won't be doing mechanical energy, so we're just going up to this spot right here. All right, go ahead and pause the video at this point. I want you to write down as best you can from your notes on your reading and watching the previous videos. How is it that you define or bring meaning to work, power, and energy? What are some applications, formulas? You could probably add in their vernacular uses. What are the units? How are they used? And then, as you see in this figure, how are they connected? All right, we're back. After looking at that, this is a cool little word map that shows definition of work. So used all the time vernacularly. So this will be a key feature really all year, but never more important than in Chapter 9 with work, power, and energy. And that is that the words are often used in regular life, but not in a physics way. So let's look at just the physics term in here for work. So force times the distance through which it acts. Again, noting that they need to be in the same plane, so in the same direction or opposite, not at 90 degrees. Specifically, the transference of energy equal to the product of the component of force that acts in the same direction of the motion, the point of application of the force, and the distance through which the point of application moves. We will continue to harp on that point. Let's look at next. Power. Same thing. All sorts of different definitions in here. To get to physics, you got to go all the way to number 15. Are you kidding me? I think we need to move this. Maybe not first, but let's get in the top 5, can we? Work done or energy transferred per unit of time. All right, so back up a little bit. We're dealing with work is force times distance. Moving down, we have power is the rate at which work is done, or work divided by time. Now, you're going to want to note force and distance are both directly proportional to work, right? More force, more work. All right? Force goes up, work goes up. If distance goes up, work goes up. Now, the formula that we're seeing down here for power is similar to something like, some other formulas that we've seen in the same shape would be velocity is distance divided by time, or acceleration is velocity divided by time, or acceleration is net force over mass, right? So we've seen those, and we studied the relationship probably most in depth when talking about Newton's second law. So how do we apply that here? That is, if time goes up, power goes down. So if it takes you longer to do the work, you're less powerful. If you do more work, you are more powerful, assuming you do it in the same amount of time. All right, so remind ourselves of the video and really how it is that you calculate this. Ultimately, it's force times the distance divided by time, seen in these icons. Energy, we'll cover a little more later, but you can take a peek at this, stop it, pause it. Physics definition, 8 out of 9. Not the best, but we'll deal with it. So joules are going to be the unit for both energy and for work. So if you zoom in on this, check it out. We've got units which match up to our formula. Newtons are force, meters are distance. Now, force comes in newtons, so Newton meters, right? And newtons are kilograms, meters per second squared. And that's times meters. So if we zoom in on that further, hopefully that sharpens up in a second. If we zoom in on that further, that gives us kilograms, meters times meters, which is meters squared, divided by seconds squared. Now that is all equal to joules. And you can see those written out in that fashion. Awesome. Joules are named after James Prescott Joule. You can see when he lived and some of the amazing things that he accomplished. And it does bring up, both with Joule and James Watt, the age-old question, which is, maybe we'll remind me to do this as a poll in class. But pause it, write this down. Would you rather have a unit named after you or an element on the periodic table? I don't know. Probably vary depending on the day. Today I want my own unit though. Say that's 7.48 centimètres or kilomètres. That's got a nice ring to it. All right, what did we just say? We James Prescott joule. Now we got the watt. Again, these are metric or System International SI units. You can see, hey, this guy is broken down. It is equal to joules per second. All right, so if we write this out, power is work divided by time. We just said that work comes in joules, time comes in seconds. All right, so we just write that J over S. And that is a watt. And that is a capital W. Big one. Not a little one, big one. All right. Now, if you look at that, okay, so we got units here. Newtons times meters divided by seconds. So we saw up earlier that newtons times meters were kilograms meters per second, meters squared per second squared. Sorry. So if you put in another second in the denominator, you get kilograms meters squared seconds cubed. Now, you do not need to memorize that. It's just interesting to know where it comes from and how it is built. All right, here's James Watts. He lived 1736 to 1819. So a power challenge. All right. So this is going to connect us back to what I did in the video here, where you are going to calculate your own power. In order to do that, what you're going to need to know is your weight in newtons, distance in meters, and time in seconds. So the easiest thing to do is climb up some stairs. Now, we took a surveying class the other day, and not everybody's got stairs. That's cool. I get it. You got to find something else. So I'm going to make a separate video that looks at this. With any luck, I'm going to be doing it outside when I'm finished with this. If you do have stairs, or if you have access to stairs, or you can climb a ladder, then this is what you'll need to know. So as with all labs, we want to think about what are we measuring, what are we calculating. So in this case, with some stairs, we want to know just your straight up measurement, height of one step. Now, to get from 1 to 2, you got to know how many steps. Now, we also want to keep in mind, say we take Sisyphus here, climbing up his mountain. Okay? So here's this triangle. I'm going to just move this over there so we can see it a little bit better. In terms of distance, so if we say that work is force times distance. We got this ball rolling up, okay? The force is the weight down. Force is force due to gravity, or the weight, which is going to be right here. But the distance really is just, oops, in this case, so be clear here, in this case that's the dy, because the weight is down, so the distance up is all that counts. So we're concerned with the y, not the x. So just this upward part. So if you run up a hill or climb your stairs, we don't care about the x horizontal component, just the y. Hence, we don't care about the width of your stairs or, the distance at, the spot that's flat. We just want to know total distance. Height, then your weight, and then the time. So if we look at this, we've got our three components right here. We've got distance, we've got force, we've got time. Force times distance divided by time. Now, if you don't have stairs, you have to do something else. And truth is, everyone's going to have to do at least one other thing. Now, to answer these questions on here, we're just doing 1, 2, and 3. So just these, we're not going to worry about 4 yet. All right, again, questions on that, put them below. I'll also make a longer video coming up. Here's some GIFs that didn't show up here, but they're of Sisyphus. Just trust me on that. All right, so we're going to look at our problems from, so if we just skip over real quick, these are the worksheet problems. The beginning ones are already solved. As with always, kind of zoom into them, cover up the answer, and do them on your own. Then you got a way to check for them. Now your homework is going to be 1, let me highlight this, 1 with Russell dragging a suitcase. Number 2 is with Katie and the cat. Number 3 is with Marissa. And number 4 is with Atlas and Hercules. Cool. Let's actually go back to these. So I set them up separately. This is just a reminder that you're going to have to make sure we distinguish between given the mass of something and its weight. Mass is not weight, and therefore it's not the force. All right, so here we go. We got example 1. Bud, a very large man, mass of 130 kilograms. I think I'm like 90 kilograms, so this guy is quite a bit bigger than me. 50 or so % bigger. Stands on a pogo stick. How much work is done as Bud compresses that spring, the pogo stick, by 0.5 meters? All right, let's label 130, 0.5. Now, what are these actual amounts? You got to make sure this is a mass. This is distance. So I want to know how much work. Okay. So first line is weight, to give you a little bit of hint here. Let's draw it out. So here's Bud. We go simple drawings again. And then here is, let's see if this works. Close enough. How about that for a pogo stick? Let me just change the color here. A little bit thicker. Oh no, not that thick. That thick and red. Perfect. Looks like a sword, but that's our pogo stick. So we know that mass of Bud is 130 kgs. Now there's a spring in here, and that gets compressed by a distance 0.5 meters. Okay, and then our work. We don't know it, but we do know that work is force times distance. We have distance, we don't know force. So the force down, so if we were to just take, say for instance, Bud himself, we know that his weight will be his mass times gravity, or 130 kgs, times 10 Newton kilograms. Should be 1,300 newtons. Right. So I'm going to just put that in there, that we know that the force of his weight, or the force of Bud, is 1,300 newtons. So we do this math, we get 1,300 newtons times 0.5 meters. Now, we should be able to do that in our head, but if not, pull out your calculator. Click off presentation mode for a second. This will give us our calculator here, and we go 1300 times 0.5. Hey! Alright, and our answer is 650 Newton meters. You could leave it like that if you want, or 650 joules. That is our work. Beauty. All right, let's go back to presentation mode. In particular, we're looking at number 2. Again, this is a reminder of video on the difference between mass and weight. So we're going to do number 2, and we'll probably leave number 3 for you guys. we'll talk about it though. Okay, so after finishing her physics homework, Sharita pulls a 50-kilogram body, her body, out of a living room chair, climbs up 5-meter high flight of stairs to her bedroom. Okay, so this is what we actually want you to do if you got stairs. If you got an ability to maintain physical distancing and do it somewhere else, then go ahead and do that. If not, come up with another way to model it. How much work does Sharita do in ascending the stairs? Again, there's only going to be work done going up the stairs, not going down. All right, so this is similar to what we just did. We've got some labeling to do. So 50 kgs. It's a mass. We know that 5 meters here is a distance. We want to know how much work. Okay. So given really the same things as last problem, we have some stairs here. Here is Sharita. We know that she has a mass of 50 kgs. Now we're just going to put this straight in her head. Her weight is therefore 50 times 10, 500 newtons. Now we also know the height of those stairs, which they tell us over here at 5.0 meters. All right. How much work does she do? So again, right now we've got read it, labeled it, draw it, our knowns and unknowns we want on the problem. We got our formula, which is work is force times distance. And again, it's not mass times distance, it's force. So 500 newtons times 5 meters, 2,500 joules, or Newton meters. You can leave it as you want. Bigger, thicker box. Okay. Let's actually just look real quick at 3 and we'll talk about it. So we got Sharita and we got 2 different scenarios. Okay. The first one takes her 10 seconds to go up those stairs. The second one, it takes her 3 seconds. So we're looking at, we're going to skip some steps. You're going to do these in your notes. So go ahead and pause it right now. We're back. We're going to look at the difference between work and power. Really, to go from work to power, you're just adding in the element of time. How long did it take? So we can go ahead and figure that if it takes you less time, you're more powerful. So on night 2, 3 seconds, she's more powerful. Knowing that our formula here is work divided by time, we already got the work done before, which is 2,500 joules. And then you're dividing it by the time. Now, the time is either from night 1, 3 seconds. Oh no, that's backwards. Night 1, 10 seconds versus night 2, 3 seconds. So we put those in our calculator and we do the necessary math. All right. Just quickly to show you, here are those solved problems we just did. Your homework is to do 1 and 2, 3 and 4. You also are responsible for getting personal power completed. If you're having trouble with that, again, check back to previous videos, and I'll put a more in-depth video on extra things you might do in lieu of using stairs, or in addition to using stairs. All right, everybody. Thanks so much. Take care. Stay safe. Wash your hands. See you later.